In the last two videos, we talked about linear functions and inverse functions. So let's quickly go over these. A linear function is a function that just has a constant rate of change and can be written in the form y is equal to some rate of change times x plus some initial value, or y equals wx plus b. An inverse function is a function that just reverses the effect of its original function. If you don't understand either of these topics, I have full videos on them. You should go check them out. So a nonlinear function is just going to be pretty much the opposite of a linear function. It's going to not have a constant rate of change, and it's also not a straight line like a linear function is. So if we draw a Venn diagram of, let's say the blue represents linear functions, and we could say red represents nonlinear functions. So there's no overlap between these two in our Venn diagram because they're exact opposites of each other. But if we were to also draw inverse functions in this diagram, it would look something like this. So some subset of linear functions are inverse functions. And same in nonlinear functions, some subset of nonlinear functions are inverse functions. The next question then becomes, why do nonlinear functions matter for AI? If you recall, like we briefly discussed, a neural network kind of looks something like this. So there's going to be some input, and for this very simple neural network example, there's just three neurons which are all connected to each other. This input is going to go into this neuron, and this neuron is going to have some function inside of it. In this case, that function is f of x. So this input is going to go here into this x, and then this neuron is going to spit out this output y to this next neuron, which internally is going to have its own function inside of it that is going to process that input. That's going to spit out an output, which is going to go to this neuron, which is going to spit out the final output. Again, for just this simple neural network example. So just to make this a little bit more clear, let's go ahead and say that the function inside the second neuron maybe is called g of x, and the function inside this final neuron is called h of x. And if we were to map out kind of what this neural network is mathematically doing, it's going to look something like this. So f, you feed some input into the function f, and that output of function f is fed to the function g, and that whole output is then fed to the function h, which then produces the final output, which in this case we'll call y. So to understand why nonlinear functions are so important for I think it's kind of helpful to do a thought experiment. So let's pretend that all three of these functions, f of x, g of x, and h of x, were linear functions, that a neural network didn't use any nonlinear functions internally inside of it. Let's say that this function looks something like this. Y is equal to w1 times x plus b1, and this internally in this second neuron, it's going to look something like this. Y is equal to w2 times x plus b2, and in this last neuron, the linear function looks something like y equals w3 times x plus b3. And again, the key thing I want to just highlight here is that these functions can be different in every neuron. So, W2 doesn't have to be equal to W3, B2 doesn't have to be equal to B1. But if a neural network only has linear functions inside of it, like these three, and we repeat what we did here and write out mathematically what the neural network is doing, it's going to look something like this now. W1 times the input plus B1, and this entire value is put into the second neuron, which then is going to be W2 times this value plus B2. And then that whole value is put to the third neuron, which is going to be W3 times that whole value plus B3. And this is going to be Y. So let's go ahead and graph this to kind of see what's going on here and what the limitations of this are. So I went ahead and graphed that equation. And again, this equation is going to represent the mathematical, what that neural network is doing mathematically. And you see something very interesting. So no matter how I change any of these variables, the W3, B1, etc., no matter how I change any of them or all of them, the output is going to be always a line, just a straight line. And that's the big intuition here is that stacking linear equations, which means, like even if you put a linear equation inside a linear equation, and even if you do that thousands or millions or infinite times, the output is always just going to be a straight line, like we see here. So just to be clear, this line here represents all the possible output values of the neural network. It's all the values the neural network can spit out. And if we change a variable or many variables, the possible values that the neural network can output do change, but they remain a line. And that's a problem because take a look at this data here. So I plotted 4 points in black, red, blue, and green, and you can see that they kind of grow exponentially. They're kind of curved up. And you can see that no matter what I do with this straight line, it's never going to be able to fit this data very well. And that's just for a simple kind of curved up line like this. Like imagine that some data points came back down and then back up again, or it had some very complex relationship. There's just no way a straight line can model those values. And that's why nonlinear functions are so important. Neurons and neural networks have to contain them to model functions that aren't just straight lines. If you're still kind of struggling to understand what I mean by that line represents all the possible outputs of a neural network, maybe a more concrete example would help. Say, for example, for the input of this neural network, we're putting in something like square footage, and the output we're expecting from a neural network is something like the price of a house. Now this might make a little bit more sense. So in this case, what it's going to mean is that a neural network can only output prices that are on that straight line. So it can say that, okay, as the house square footage increases from 1,000, 2,000, 3,000, 4,000, it's just going to have the price increases be at a constant rate of change in a straight line. However, in reality, that might be a much more complex relationship that isn't just a straight line. And that is why this internal function inside each neuron has to be a nonlinear function.